Okay, so we're in 7.2 now. Still working on developing techniques for evaluating different types of integrals. The focus in this section is dealing with integrals of functions that consist of trig functions, sine, cosine, secant, tangent, that kind of a thing. And the majority of it is actually focusing on trig functions raised to some power. So we're going to start by looking at a general strategy for solving these types of integrals, and then we'll work through some examples. So the first strategy we're looking at is what to do if you have an integral of a function that looks like sine of x to some power and cosine of x to some power being multiplied. So sine to the m of x, cosine to the n of x, whatever m and n happen to be, they're going to be integer powers. What do we do as kind of a general strategy here? So we break it down into cases because depending on the powers themselves, m and n, specifically depending on if one of these is not positive but odd or even, that kind of affects how you approach the integration itself. So let's begin with this first case here, case A. Looking at the cosine power, if your cosine's power, the n here, is an odd number, then what we do is we save one factor of cosine and we use that as a du in a u substitution. So if you notice here, I have sine to the power of m of x times cosine, and then the power looks like 2k plus 1, because if we have an odd number, it can be represented as 2 times an integer plus 1. That's where that's coming from. And we're going to take one of those factors of cosine and sort of push it out and leave it off to the side here. And then what we're left with is just cosine of 2k once we do that. But you can take the k and bring it out so you have a power to a power here. So now what we end up with is sine to the m of x, which has not changed at all. Cosine squared of x all to the power of k, which is the same thing as cosine of 2k. And then this final extra factor of cosine of x that we sort of saved off over here. The reason we're doing this is because we have a trig identity, the Pythagorean identity, which allows us to turn this cosine squared into a 1 minus sine squared of x. So now what we have is a big expression here where you're seeing sine of x show up in a couple of different places, which suggests that we should use u equals sine of x as a u substitution. If you do that, then your du would be cosine of x dx, which you specifically set this cosine of x out here aside so that it could act as your du in that u substitution. So we'll do examples. I want to make a note here. I copied and pasted this from our book. So when you see stuff like this, see example 1, that's referring to the actual text itself, not an example that we're going to do here necessarily. So this refers to stuff in your book, not our lecture notes. Okay, case B. If instead of the cosine having an odd power, if the sine has an odd power, we do basically the same thing, except this time we're going to reserve a factor of sine of x for our du. So we take one factor of the sine of x out, and it's going to just sit by itself over here, which leaves us with now what would be an even power of sine, allowing us to write sine this way, sine squared of x to the k, whatever that k was there. And then you use your Pythagorean identity. Again, convert the sine squared into a 1 minus cosine squared. Now I have a big expression involving just a bunch of cosines of x's to powers. And that would suggest that I use u equals cosine of x. Du would be negative sine of x, which is basically what we have here with the exception of the negative. And as you know, that's easy to account for. So this is a good strategy here. Both of these cases, case A and case B here, relied on having an odd power for one of our sine or cosine functions that appeared up here in the integrand. And that's necessary because that's what allows you to take one extra factor of either the sine or the cosine, whichever one had the odd power, and shove it out to the side, leaving you with an even power, which ultimately led to this application of the Pythagorean identity. But what if neither your sine nor your cosine has an odd power? In those cases, you can still use some trig identities to kind of simplify things, but it's also oftentimes useful to make use of the power reduction formulas for sine and cosine, and those are these identities right here. You learn about these in trigonometry. We're not deriving them here because you should have already done that in a previous class. But sine squared of x is equal to 1/2 times 1 minus cosine of 2x. Cosine squared has a similar one with a plus here instead of a minus. Those are going to end up being useful. And then there's a mention here that sometimes, in some cases, it's also useful to use the double angle identity for sine of 2x, but represented this way, where you can take a product of sine of x and cosine of x and represent it as just 1/2 times sine of 2x. There are some cases where that's really, really helpful. So we spent a bunch of time going through this general strategy, but it's really not going to start to stick until we do some examples. So let's just start with one example. Here we have sine cubed of x. We want to evaluate this, the integral of this function. So this is a sine function raised to an odd power. The general strategy for that is to take one factor of your sine function and push it out here with my dx. So now that I have this extra factor of sine saved, my new power up here is a 2, sine squared of x times sine of x. Then you take that new even power of sine of x and use your Pythagorean identity on it. So I can rewrite that as 1 minus cosine squared of x, sine of x dx. And here's where we're setting ourselves up for a u substitution. In this case, I would let u equal cosine of x, in which case du would equal negative sine of x dx, okay? I almost have that, but the minus here isn't showing up here. So we manipulate this a little bit and multiply both sides of this thing by -1, so that now my sine of x dx can be substituted out for a negative du. I'm going to take the negative completely out to the front of my integral, and now what I have in parentheses here, this would be 1 minus u, because that's cosine, squared. And then this whole thing here, coupled with the negative that I accounted for, is going to give me my du. And at this point, it's a really straightforward integral, right? So I have negative u minus 1/3 u cubed plus c. And then I'm going to substitute my cosine back in for these u's. And I'm also going to use this negative here to switch the order of subtraction that I'm looking at. So a couple of steps in one here. I'm going to have 1/3 cosine cubed of x minus cosine of x plus c. Okay, so the strategy helped out a lot there. And this one wasn't really all that bad. Not too many steps in this integral. Let's try another one here. Okay, this one looks more complicated. Not only do we have both a sine and a cosine showing up, which we didn't have in the previous example, the argument, or the thing that's showing up inside parentheses, is a little more than just an x. It's an x over 2. That actually doesn't make it all that much more complicated. It's just one small layer that's being added to this example. So let's still approach this with the same strategy that we talked about in the previous page. I have an odd power on one of my two functions here. It's on my cosine. So I'm going to do kind of what I did before, reserve a factor of cosine and kind of push it out to the end there. I'm going to write this as the integral of cosine squared of x over 2 times sine squared of x over 2, and then I have this extra cosine of x over 2 that I floated out to the end there. Okay, now remember, the idea is to take that cosine that we pushed out here and have that act as our du, which means I would like my u to be a sine function. So this cosine squared that was left after moving this extra factor of cosine out, I'm going to use my Pythagorean identity on that. So that will look like 1 minus sine squared of x over 2 times sine squared of x over 2 cosine of x over 2, like that. Okay. Next up, what am I going to want to do here? Well, I have a u substitution that's going to help. I'm going to set u equal to sine of x, because that's what's showing up in this first part of my expression here. Then my du, sorry, I need to be a little bit more specific, sine of x over 2, not just sine of x. What would my du be in this case? Well, it's not just cosine of x over 2, it's 1/2 cosine of x over 2, and that's because, my dx right there, that's because we have a composite function. X over 2 is on the inside, cosine is on the outside. I would have used the chain rule there, and a 1/2 is what would have popped out. Okay, I don't see a 1/2 cosine of x over 2. I just see cosine of x over 2 showing up here. So I'm going to multiply both sides of this by a 2. So now I have exactly the expression that's appearing here. I can substitute a 2 du in for that. Let's bring the 2 out of the integral. And what am I left with? I have 1 minus u squared times u squared. This becomes du. I've accounted for the 2 over here. Okay, this is straightforward to evaluate. I'm going to distribute my u squared in. U squared minus u to the 4th du. And easy integral now. It's 2 times 1/3 u cubed minus 1/5 u to the 5th plus c. I'm going to do a couple of steps in one here. I'm going to distribute the 2 in for one thing, and then I'm also going to swap my u's out for the sine of x over 2 that I had set my u equal to. So doing that now, hold on, double check something here. Oh yeah, okay. Doing that, I would end up with 2/3 sine cubed of x over 2 minus 1/5 sine to the 5th of x over 2 plus c. And sorry, that's 2/5, not 1/5, because that 2 is going to hit that 1/5 right there. This would be the final answer for that one. Okay? So far, so good. Let's do one more where we're dealing with sines and cosines, and then in the next video in this section, we'll start looking at other trig functions. But here I'm dealing with the definite integral now from 0 to pi of sine squared of x times cosine to the 4th of x. So I don't have an odd power on either of my trig functions now. So that whole business of saving one factor from one of our sine or cosine functions to use as a du is not going to work at this stage. We need to do something else first. Now, our little strategy did say that we can use those power reduction formulas to make this simpler, but you don't necessarily want to do that as a first step. Sometimes that's a step that comes a little bit later in the process. So what I'm going to do here, I'm going to try something a little bit different. I am going to use my Pythagorean identity on the sine squared that's already showing up there. So this is going to give me 1 minus cosine squared of x, and then I have this cosine to the 4th of x dx showing up right there. Okay? And now what I want to do is I'm going to do actually 2 steps in one here. I'm going to distribute my cosine to the 4th of x in, so I would end up with cosine to the 4th here, cosine to the 6th power here, but then I'm going to split it into 2 separate integrals. Actually, you know, I come to think of it, I don't really even need to do that. Let's just leave it as one integral. You can, but I think it'll give me a little less to write if I leave everything in just one integral. So this becomes cosine to the 4th of x minus cosine to the 6th of x dx. Okay? Now, it's at this point where it's going to help me to start using some of the using those power reduction formulas. So notice if I were to write cosine to the 4th as cosine squared of x squared minus cosine squared of x cubed. That would give me this cosine to the sixth here. I can start to use my power reduction formulas on each of these cosine squareds here. Okay, so let's do that. My power reduction formula, this goes from 0 to pi. It's going to look like this. The cosine squared in there is going to turn into 1/2 times 1 plus cosine of 2x. And we are squaring that. So I'm ending up with kind of a lot of parentheses and whatnot here. Those things will kind of simplify out in a little bit. Let's do the same thing here. This cosine squared of x will turn into the same thing. So I'm going to have minus 1/2 times 1 plus cosine of 2x. And then this whole thing is getting cubed like that. All right, now let's think about what this would look like. I have to square this whole thing. So 1/2 squared is going to be 1/4. I'll have a 1/4 here. When I square this is like a binomial. It squares the way a binomial would. So I'm going to get 1 plus 2 cosine of 2x plus cosine squared of 2x. Okay. Now I'm going to do the same thing here. I'm going to cube this guy. So I'm going to have minus 1/2 cubed is 1/8. And then when I cube this, I'm going to get 1 plus 3 cosine of 2x plus 3 cosine squared of 2x plus cosine cubed of 2x. By the way, if you're looking at this and thinking, how can I get this so quickly? You go back and revisit your binomial theorem from algebra. That would have been an intermediate algebra concept. You may have also talked about it in a pre-calculus class. It's a way of expanding binomials to some integer power in a somewhat quick way. That's what that would come out to. It's good to have that in your tool belt. All right, now there's kind of a lot of combining of like terms and things to do here. So I'm going to try to do a few things in one step. So let's see. I have constant terms. I have cosine of 2x, cosine squared of 2x, and cosine cubed of 2x. Those are all different types of terms showing up here. I'm going to want to combine all of this stuff. So let's deal with the constants first. 1/4 times 1 minus 1/8 times 1. That's 1/4 minus 1/8, which is just 1/8. That's going to be the new constant term. Look at my cosine of 2x term. So 1/4 times 2 is 1/2. And then I'm going to have minus 3/8 cosine of 2x. That's going to be the next cosine of 2x term that shows up there. 1/2 minus 3/8 is 1/4. So for that, I'm going to end up with, make sure I'm doing that right as well. Yeah, I should end up with plus 1/4 cosine of 2x. Okay, next up, I'm going to have 1/4 times cosine squared minus 3/8 cosine squared, which would give me negative 1/8 cosine squared of 2x. And then there are no cosine cubed terms here, so it's going to look like a minus 1/8 cosine cubed right there, minus 1/8 cosine cubed of 2x. Okay, so far so good. I'm gonna check something here. 1/2. I think I made a mistake here. I said 1/4 times 2 would be 1/2 minus, this would be 3/8. Yeah, 1/2 minus 3/8 should be 1/8, not 1/4. Turns out that's actually not going to matter, because regardless of what this constant is, this thing's going to end up being a 0. Okay, now I've got a little bit of an issue here, because it looks like I am dealing with a lot of cosines now, where I do have cosine squared, for example, cosine cubed. I want to point something out, though. I know without having to really do any real work that when I integrate this particular term from 0 to pi, it's going to be 0. Now, how do I know that? I'm going to talk through that for a second. Think about what one cycle or one period of a cosine or a sine function looks like. Okay? So here is like one period of a cosine function. I'm going to have exactly the same amount of positive area here as I do negative area here because of the periodic nature of this and the symmetric nature of this function here. So the total area over one period of that cosine function is 0 because the positive area will cancel with the negative area, right? So if you know what the period of your sine or cosine function is, and you happen to be integrating over that period or over some multiple of that period more generally, you know for sure that you're going to get all of this canceling area from that definite integral. Well, if I have cosine of just x, the period of that would be 2 pi. But if I have cosine of 2x, that 2 there is what we divide our 2 pi by to get our new period. 2 pi divided by 2 is just pi. So what that tells me is that the cosine of 2x function has a period of pi. From 0 to pi, we go through one full period of that function, of that graph. And that's exactly what we're integrating over. So knowing this, having this kind of intuition about the sine and cosine functions, right away tells me that integrating that thing is going to go to 0. Now you can do the more lengthy actual antiderivative using the fundamental theorem of calculus and all that jazz to show that this is 0. But why do all that if you can just zero it out right away? Okay. Now here's another thing. I have a definite integral where a constant is part of my part of the thing that I'm trying to evaluate. A nice thing that we know about integration is if you do a definite integral over some interval of a constant function, the answer to that, the solution, is always going to be that constant times the difference between your limits of integration. 1/8 times, in parentheses, pi minus 0, which is just pi. So this term is going to become pi over 8, and this term is going to go to 0, right? So now what I have is just these two remaining terms right here, and I can manage each of those on their own. Notice both of them have a negative 1/8, which we might as well just pull out completely. And now I have an integral from 0 to pi of cosine squared 2x plus now, because I took a negative out, cosine cubed 2x dx. Okay? We are going to deal with each of these separately. So what I'm going to do is think of that as two separate integrals. I'm going to have minus 1/8 here. I'm going to take an integral from 0 to pi of cosine squared of 2x, but let's right away use our power reduction formula on that. That's going to be 1/2 1 plus, not cosine of 2x, cosine of 4x. When you apply this power reduction formula on these sines and cosine functions, this angle here, or this argument for your cosine function, is always double the one that you started with where it was cosine squared. So that would give me 4x there. Here, I have plus cosine cubed of 2x. So let's think about what's going to happen with that. This fits into one of those other cases where now I have an odd power of a cosine function. What I can do is save one power of my cosine function, cosine of x. Notice I'm giving myself a little space here. I'm kind of pushing that out. And when I evaluate this, I'm going to have a cosine squared left. But let's go ahead and just in this step, convert that to 1 minus sine squared of x, since I already know that's where we're going with this. Okay? All right. Let's see. I'm very short on space here. I'm at the bottom of my page. Let's see if we can fit this in. Pi over 8. minus 1/8. What do we get from this integral right here? When I distribute that 1/2 in, I'm going to get just 1/2, right? And then when I integrate it, I'm going to get x over 2. So x over 2 is what that 1/2 becomes. Then I have 1/2 plus cosine of 4x. When I integrate that, I would use a very simple u substitution, set the 4x equal to u, du is equal to 4, and so on and so forth. But what that's going to end up giving me is, well, actually, it doesn't matter. Doesn't matter. I don't need to go through all of that work, because once again, what is the period of this cosine function? Cosine of 4x, its period would be 2 pi divided by that 4, which is pi over 2. And if we're integrating from 0 to pi, that means that I'm going through 2 cycles of that cosine function. The first cycle gives me a total area of 0. The second cycle will give me another total area of 0. So altogether, that is going to go to 0. Multiplying it by 1/2 doesn't change that, because all that does is that compresses the graph vertically, but we still have 0 area in total. So that is just going to give me this x over 2 right here, which I evaluate from 0 to pi. Now what about this guy right here? For this function, I would use a u substitution. U is equal to sine of x, which means du equals cosine of x dx, which I have right here. Let's convert everything over into u's, plus the definite integral. This 0 and this pi also have to convert to u values. So I have to plug 0 into this function, and I have to plug pi into this function. And I just realized, you probably already caught this, I forgot that I was dealing with a 2x here, not just an x. So I do need to make sure that I'm including 2's here, which means that I'm also going to have, in my du, I'm going to have a 2 right there, which I would multiply both sides of this by 1/2 to produce a 1/2 right there. So I caught myself with that mistake. I wish I had caught it earlier, but that's okay. And I realize this is now kind of sloppy, but don't worry. Let's think about what's going to happen here. That's a 2x as well. That's a 2x as well. I'm integrating this function with a u substitution, which now looks like 1 minus u squared. And then I have a du, and I also have this 1/2 out here. My limits of integration, if I plug a 0 into sine of 2x, I get sine of 0, which is 0. If I plug a pi into sine of 2x, I get sine of 2 pi, which very conveniently is also 0. Now, it does not matter how complicated this integrand is, because if I integrate anything from a number to that same number, we know in Calculus 1 that this whole thing becomes 0. So don't waste your time evaluating that directly, okay? Now let's wrap this up. I have pi over 8 minus, I can see that plugging a 0 in here gives me nothing, so I'm going to plug a pi in there, and that's going to give me 1/8 times pi over 2. That would give me pi over 16. Pi over 8 minus pi over 16 is pi over 16. So that one took considerably more work, more time, and I had made a couple of mistakes that I sort of corrected along the way, which you're going to find yourself doing a lot of too. But let's leave this one as it is, and in the next section we'll start looking at different trig functions.